So good evening everyone. So welcome to the seminar series on exploring nonlinear dynamics from basics to applications. So we are on the session 9 of this series, and in the previous session 8 we have looked into the chaos theory. So did you watch the chaos theory lecture, or you have seen the videos which we were discussing last time? Oh, okay. So then so this session we will be discussing continuation of that. So I will give it just, okay, by the time Joe comes, I will just explain the previous thing once, and then we will, because you need to have some knowledge of what we are talking of, else you will not understand that. Yeah, so these are the books and references you can check, and videos for reference. Yeah, so we'll start with the session 9. And so in the previous session, so we were talking about the topic called chaos, and so there the chaos was initially, or the term got famous by a person called Lorentz, and he derived a three-dimensional system from a simplified model of convection rolls in an atmosphere. So how the rolls, due to the temperature difference from the land and the atmosphere or the surrounding, there is a convection happening. So this convection rolls, he was trying to model it, and he came up with a three-dimensional model. So that model is what we call Lorentz equation. So okay, I will just share the screen here once. So we were discussing on the topic called Lorentz equation. So the equation is a simple three-dimensional equation, which is x dot is equal to sigma times y minus x, y dot is equal to rx minus y minus xz, and z dot is equal to xy minus bz. So the important thing to note here is the nonlinear terms which you can see here is this xz and xy. So these are the two nonlinear terms, and he was trying to model the convection rolls in the atmosphere. So he was interested in weather prediction. So he wanted to understand why there is so complication in predicting the future of a weather conditions in a state or a country. So he developed some small model, and this simple looking deterministic system, it can have very different variety of dynamics it can show. Not only simple circular motion or a periodic motion, not only that, it can show wide variety of irregular dynamics also. So that's why this equation became quite famous in that. It was in 1963, so that was quite famous at that time. And so based on this Lorentz equation, there are certain simple models that was there are certain models or experimental methods were shown by people. So I will just show those videos. So based on this similar to this simple three-dimensional equations, there were certain experimental models or experimental work that was carried out. And so out of that, first one is what we call the water wheel, a chaotic water wheel. So we will just see how that works. Yeah, so this is one of the experimental setup which shows this kind of erratic behavior by the simple model. So the experimental setup here is, you have a different pulleys being connected over a wheel, and so they will show you that this each bucket has a, so they will show you in zoomed version here. So each bucket here has a small hole at its bottom, and you have a bucket being kept on each hand of the wheel. Now when you open so they have a motor system also here. So this is the motor system, so where they pump the water at different speeds. Now what we expect is, when your water is coming, it takes certain time, and once the bucket fills, it will start rotating in one direction. But we will see what happens in such a situation. So now they have on the motor and water has started falling, and slowly the bucket starts filling up, and you can see one. So now the wheel has started rotating in the counterclockwise direction. Now this motion, see, similar to what the model, or a simple model which we has derived. This also shows some similar dynamics at a particular rate of the flow rate of water. Now if you see carefully, now the system reverses itself after certain time. Now it shows a very different behavior. It goes forward, it goes backward, and it's complete. So this is what we call chaotic. It is a deterministic system. Actually, you can use the model and predict the different states of the system, but due to small change in the initial conditions of the water what we are sending, whole dynamics, the rotation of the wheel is completely changing. It's sometimes moving forward, sometimes moving backward, and you are not able to predict it completely. So this sensitive dependence on this initial conditions is one of the characteristics of a chaotic system, and it's one of the characteristics of chaos. And so I will just fast forward. So here he shows 4 different cases where they start at different values of water, and you can see now slowly the water has started, and each of them each is at different conditions. Very minute change in initial conditions can also trigger the system to very different final states. So there you can see the first and the fourth are rotating clockwise. Now the third has stopped, third has even reversed, now fourth has reversed. So a small change in this initial condition is resulting in wide variety of dynamics that we can observe in a practical system. So this is the simple experimental setup which is present, called the chaotic water wheel. So what is chaos here is the irregular dynamics shown by this wheel or its rotation in particular direction. If you measure, if you plot the time series of that rotation, you can observe that it's not follows a particular path, it reverses or it changes its path very randomly. So that's one of the example. Were you clear with this example? Okay, so this is simple one example, and based on this, one more experimental setup was created in MIT, and this is what will be mentioned in the books of Strogatz, called, so it's a tabletop experiment. So this is Stephen Strogatz himself. He will mention it in some of his videos. So this is the chaotic water wheel. They have it in MIT. So this is the water wheel they mention here. So I will just explain the different components here. So you can see these are the different columns that are present for the system. I hope my cursor is visible. Okay, so these are the different columns of water which you can fill in each of these columns. These are transparent, and you have a manifold being kept over this. You can see this manifold, black color thing, through which the water comes in, and you have holes in this manifold through which the water fills in each of these columns, and the water is colored with a food color so that we can see the water is being getting filled. And at the bottom of each of these columns you have holes being provided for the water to drain down, and this black colored thing is a wheel like thing. So you can rotate. So based on as a base on this, this wheel, this transparent thing will rotate, and this is the brake. So they say this as a brake where, sorry, an experiment is going on. Yeah, okay, sorry about that. And so they call this as a brake where you can tighten the brake. If you tighten the brake, this wheel will rotate very slowly, and if you loosen it, it can rotate very freely. So that's one of the control parameter. And the wheel, so this black colored thing can be lifted up using a motorized thing. So that's this part. So you can align it into a particular angle. So that is another control parameter. Now if you change this angle, it will determine, it will change the gravity on the liquid column, and if you apply more and more brake, it changes the with how much energy the system can rotate and all. So these are the two control parameters. Now what he does is, so now he shows, I will open the caption to see what he says. So now he on it, and you can see from this manifold the water is slowly getting filled up in each of these columns, and after that it gets drained out because you have a hole at the bottom. So the water gets filled through the nozzle and through this chamber holes, and they drain down. So now he keeps the brake at a particular direction, and he rotates that, and now the water is, you can see that the water slowly gets filled uniformly in different columns, and it rotates in one particular direction, and you can see there is, the water is getting very smoothly, it's getting filled up. So the brake is not so much tight, that's why you are able to get all the water being filled uniformly. So even if he rotates in the other direction, you can see that still the water is getting uniformly filled, and the system is rotating in one particular direction. Now he tightens the brake a little bit more, and now since the brake is tightened, you will see that the system remains at that particular state for some time, and once it's getting more filled, you will see that the system rotates in one particular direction. And now this is one particular state of the system, it gets filled and it rotates in one particular direction. And now it gets filled and it goes back in the reverse direction. So now this, it goes back in the towards the left, and it gets filled and it goes towards the right now. So this is completely, now it's a deterministic system, but still the brakes, a small change in the control parameter was able to cause different dynamics, and you can see that the system moves in different ways, that too without, we are not able to predict it properly. So its behavior, you can see, observe that it changes completely up and down. So he loosens the brake a little bit. Now the wheel can rotate a little much more freely, and we observe system rotates and it now it goes back. Yeah, so now it went twice in that direction, goes once more, and now yeah, so this is a example of this chaotic system. Yeah, so these are the two analog systems for this simple Lorentz equation which we have mentioned, and we were discussing this in the previous section. And if you derive the equations for this simple system, say so the last shown analog of this Lorentz system, the chaotic water wheel, which we just showed. So if you derive the equations for those finally, you will be ending up into a similar equation like, so I am just showing you how it is analogous to the Lorentz equation. So the final equation, so B1 A1 are all parameters which are there in the system. So we don't need to, okay, you don't need to worry much on how it's derived here. Our interest is what is chaos and how we are addressing that. So this is RL by L. So this is the final equation which you will get if you are trying to derive that Strogatz water wheel that is there in MIT. If they used the different conservation equations and amplitude equations they used, so that derivation is given in the book. So they used that and the conservation of energy, torque balance and amplitude equations to get to this form, and this is similar to the form of Lorentz system. So that's why we say it's an analogous to the Lorentz equation. Now we were interested in to say that for such a system, chaotic system, last session we derived a certain statements. That first one was these equations were symmetric. That is, if you replace this x, y and z by minus x, minus y or minus z, still your system shows the final equation will remain the same. It does not change. So that is one thing which we have said. And the another one was, so most of the systems in real world are dissipative in nature. That is, there are a lot of factors that can dampen your system. It can reduce your energy. If you have certain energy, over a time your energy will decrease. So that's what we call as dissipative systems. And we see that Lorentz system is also a dissipative system. So by dissipative system, in nonlinear terms, we mean that the volume of the attractor or the phase space, it decreases as you are changing the control parameter. So what we were able to show was, okay, in short, if I say we had a volume of the say we had a big volume in which your phase space was there, and we consider a surface S in that, and over a time delta t, if we say that this surface is increased by say delta S to S t plus delta t it went, then the volume, say this was our initial volume v of t, so it normal vector is n, and say if S is your trajectory, then you will have a velocity f, instantaneous velocity f in that. So we want to see if the volume increases or decreases as time is progressing. If the volume is decreasing, then you can say that it is a dissipative system, because over a time its values is, its whole phase space is getting decreased. Now if you consider that case, we derived this, so we checked the volume at a given time, and we checked the volume at Vt plus dt. Okay, okay, I will just write it down so that you will understand. So the actual Vt plus dt was nothing but V of t plus the volume swept by tiny patches. So the tiny patches means we take a small section of this, so this velocity times the normal vector will into dt will give you the distance it has moved, and this small area be the dA, delta A be the area change. Now so that volume after t plus dt time is nothing but the volume at that present time plus the integration of over the total surface. So for a small surface we show that it is velocity into the normal vector times the dt over the small area dA. If you do, we can add that up. So if you rearrange it, v of t plus dt minus v of t is nothing but over the surface integral f dot n dt times dA. Okay, so now if you bring the dt also down here, minus v of t by dt is nothing but the surface integral of f dot n dA. So this is now a familiar term. So this is what our standard differential equation says, that is v dot f of x plus dx plus minus f of x by dx will give you the derivative of the system. So this will be equal to, now this term is a surface integral, and by a theorem called divergence theorem we can convert this into a volume integral. So if you convert it into volume integral, instead of f into normal vector we will take the gradient of the f over the total volume dV, that small volume. So here if you see, del dot f is nothing but dou by dou x of f plus dou by dou f of y of f and dou by dou z of f. So f here is our equation which we have seen, that is x dot is equal to sigma times y minus x, y dot is equal to rx minus y minus xz, z dot is equal to xy minus bz. So f is nothing but x dot I cap plus y dot j cap plus z dot k cap, and if you take the dot product of that, so you will be getting with dou by dou x of x dot plus dou by dou y of y dot plus dou by dou z of z dot. So dou by dou x of x dot is nothing but sigma times y minus x plus dou by dou y of y dot is nothing but rx minus y minus xz, and dou by dou z is z dot and dou by dou z of z dot is xy minus bz. So now derivative of y so it's a partial derivative, so y will be constant, so you will be left with only minus sigma x in the first term, and in the second term only y terms you need to take, so that is minus 1 plus dou by dou z of minus b. So if you take this, it's nothing but sigma x plus 1 plus b. Okay, when you are taking derivative, this will be so you are left with finally, this implies del dot f is nothing but minus of sigma 1 plus b. So your v dot equation was volume integral of del dot f into dv, and if you integrate over the volume, minus of sigma plus 1 plus b times dv if you do. Now you are left with final equation is minus sigma plus 1 plus b are constants, and finally you will get some v value, say that. So this is now simple equation x dot is equal to x form. This you can write just dx by dt is equal to x and dx by x equal to dt, and if you integrate it, you will get log x equal to t plus c, and x is nothing but e to the power t. So here finally we will be getting is v of t is nothing but some initial value times e to the power minus sigma plus 1 plus 1. Okay. So now you can observe that this is our volume expansion equation that we have. So from this we can conclude that volume in phase space shrink exponentially. Exponentially since, because why we are saying exponentially it decreases, because you have a minus sigma plus 1 plus b into t, so that's the reason why. So this finally tells that the Lorentz equation which we are having, it's a dissipative system, and this is one of the characteristic of this equation. So one important effect of this is the volume constraint imposes a constraint on the possible solution, because now your volume is very constrained, it can only decrease, we have proved. Solutions of the Lorentz equation. So now we need to know what are the possible equations, and we need to see if the properties which we have seen in the experiments, that randomly it goes up and down, is it a chaos, or is it having a, or is it a simple periodic orbit or not, we don't know now. So we need to check, we need to prove that these are different states that we have studied till now. So that's our motive, and so in that, the first part we will be checking is, we need to check, say that if Lorentz equation has no quasi-periodic behavior or quasi-periodic solutions. Okay, so by quasi-periodic solutions, so I think quasi-periodic solutions you may not have read that. So in short, quasi-periodic, so we were discussing different dynamics of the system, and for a quasi-periodic system you had a ratio of omega 1 by omega 2 as p by q, and if this ratio is an irrational number, so what we mean by omega 1 omega 2 is, you had a coupled oscillator. So if you have a coupled oscillator, say theta 1 dot is equal to some function of theta 1 and theta 2, and theta 2 dot is a function of theta 1 and theta 2. So this rotates at omega 1 and this rotates at omega 2, and if the ratio among their frequencies is an irrational number, then we say that your system exhibits a quasi-periodic behavior. And for a quasi-periodic behavior, say these two things can be assumed, like you have a ring and you have two people running around this track, and this is theta 1 and this is theta 2 if you see, So now they are rotating at speeds theta 1 dot and theta 2 dot. Now this is how you can visualize it. And if we want to plot the phase portrait of this can be phase portrait on a what we call as torus. So you need to consider theta 1 is rotating at certain revolutions and theta 2 is rotating at certain other revolution. So this is the omega 1 and omega 2, that's why we are drawing two different circles. So by the time theta 1 rotates one revolution, how many revolutions did theta 2 rotate? That's what we have shown here by the ratio omega 1 by omega 2. And if this ratio turns out to be some irrational number, then you will get your phase portrait will not be on a uniform thing, but it will be on something what we call as torus. So it's like this, its shape will be looking like our donut. So it will be like this, and any point that starts over here, it will go like this, then it will move like this, and it will come. So by the time it revolves 1 theta 2, there is a certain number of revolutions it has completed in theta 1. So this is the theta 1 direction. So this ratio, if it's irrational number, we say we shows a quasi-periodic behavior. And our question now is, will the Lorentz equation have any quasi-periodic solution or not? So that's the first question. And to prove this, we do it by a contradiction method, which we have done similarly in previous classes. Here what we do is, if there was a quasi-periodic behavior, if there was a quasi-periodic solution in the solution, then the surface on this torus, that is, the solution should lie on the surface of this torus. That's the phase space of this system. So the solution should lie on the torus phase space. So on the torus it should lie, that is on this, anywhere somewhere it should lie here. But we have proved just now that the volume of a Lorentz system, it's decreasing. That is, it's a dissipative system, so its volume keeps on decreasing. But if the volume inside the torus would be constant in time, this volume inside the torus, it will be constant every time, it will not change any point. So this contradicts the statement that we can have a quasi-periodic solution. So we'll just write it down. So but the volume in a torus remains constant, whereas for Lorentz system the volume decreases. So these two contradicts. So we can say that there cannot be any quasi-periodic solution for Lorentz system. So that is one of the things which we have shown. And the other thing is, can the Lorentz system, or it is for the Lorentz system to have any repelling fixed points or repelling closed orbits, does it have? So next question is, Lorentz system, does it have either repelling fixed points or closed orbits? So we are slowly eliminating all the possible non-possible solutions we are eliminating for the Lorentz system, and we are finally coming to what are the possible solutions we want to see. So how to show that the Lorentz system does not have any fixed or repelling closed points is, say if you are, so by repeller what we mean is, any trajectory you are taking, if you are taking the vector, it will be thrown out of this. As time progresses, this will be moving out. Now if you are repeller, if you are considering, if your fixed point is having a repelling fixed point, then the volume will increase instead of decreasing. So if you have a repeller being enclosed within a surface, say it's a closed surface, and any condition where which starts here, it will be moving out of this surface. So this contradicts the theory, contradicts our theory of dissipative system, that volume should be decreasing. But if you are having a repelling fixed point or an unstable node or an unstable fixed point or a repelling closed orbit you are having, the volume inside the surface would increase. Inside the surface would increase. This contradicts our statement that volume should contract for the Lorentz system. So we can say that Lorentz system will not have any repelling, so we can conclude that Lorentz system can't have any fixed or closed repelling orbits. Now when we are eliminating, there is no quasi-periodic solution and there is no repelling solution for the system, then we finally come into the fixed points which are possible for the Lorentz system is either it should be a sink. By sink we mean it's a stable node, or it needs to be a saddle point, or it can be any closed orbits. It should be stable closed orbits, not unstable, because we have removed the repelling closed orbits condition. So these are the possible fixed points that a Lorentz system can have. Now we came to know that the Lorentz system can have most of these three fixed points. So if we try to solve that equation, so here we have that equation x dot is equal to, so here we have written this. So from this equation, if we try to equate all these to 0 and get a solution for this, we will see that you can have three different solutions, where the first solution can be, if you are having all the terms x star, y star and z star is equal to 0, 0, 0, then you will have a fixed points for these parameters. It is the case where the wheel is motionless. That was, wheel was standing still there. Now when your R increases, so when you are in this equation, when your R term is increasing, and we particularly say that when R is greater than 1, there is a birth of symmetric, so we will have a symmetric pair of fixed points we will have, and when this pair of fixed points will be of the form, say plus or minus b into r minus 1, and at the same time z star value will be r minus 1. So what happened was, so Lorentz called this as C minus and C plus. So where C minus and C plus represents the left running and right running convection cells. So it's like left running and right running convection cells is what he meant by the C minus and C plus. Now since we have learned any equation, these kind of things if we are getting, we will do our basic stuff called the linear stability analysis. Now if you do the linear stability analysis on this, you have the equation, say x dot is sigma into x minus y dot is equal to rx minus y, because so we are neglecting the third term because it's a non-linear term, and in linear stability we don't consider the non-linearities here, we stick to the first order things. So it's like, and we are removing here also one non-linear term was there, that also we are removing. So finally this is the linearized equation for this Lorentz system, and we observe that this xz dot is equal to minus bx, this is a uncoupled equation, so you can independently solve it, and you can see it's a simple equation, z dot is equal to minus bz. So that means you are exponentially decreasing fast, so you are exponentially decaying fast in the z direction. And for the other two equations you can write the similar form, matrix form, which we have written, that is x dot y dot, and this is minus sigma, and here it is sigma, this is r and minus 1 over x comma y. Now if you solve it, we usually find the trace of the system, which is minus sigma minus 1, which is less than 0. So I hope you remember this diagram. So this was our determinant and this was our trace, and the determinant of this is nothing but sigma times 1 minus r. Now if your r is greater than 1, then at the point 0 comma 0 you will see that your determinant is less than 0. So determinant less than 0 is in this region, which is a saddle point. So, and if you look into this, the x and y and z directions, when we are looking at, we see that z is in negative, so that is it is decreasing in one direction, whereas x and y coordinates, when you are taking, they are having a saddle node, so one is coming towards the fixed point, other will be going away from fixed point. So totally you have two incoming directions and one outgoing direction. So these kind of things, these two different things, we call it with a different names, we will just talk about that. Now we just want to see what happens if r is less than 1, then all directions are, so if you step r into this less than 1 into this equation, all are positive. So finally you will get all directions are incoming, not each one increasing or decreasing, and we will see that the origin is our stable point. Stable point. For r less than, so this you can just try to write the discriminant of it, and you will find that the total value is coming to nearly a positive value, which is greater than 0 at origin for r less than 1. So that's why we call that all the lines that are coming towards the fixed points, all are coming towards the fixed point, and we are getting origin as a stable point. So this matches with our theory of finding that you can't have any quasi-periodic solutions, or you can't have any of the rippling stable or rippling stable fixed points or closed orbits, you can't have. So we say that the two things which you can have is a saddle point, or you can have a stable node at the origin. Now, yeah, are you following that, or is it clear? Or? Okay. So another thing which we need to understand is, so when we are saying r is less than 1, each trajectory approaches the origin. So as t tends to infinity, each trajectory approaches to origin. So this means the origin is a globally stable. When r is less than 1, origin is globally stable, because anywhere you start, you are eventually coming to the origin. That means there are no limit cycles or chaos for when you are having r is less than 1. In order to prove that, we consider the usual method which we have learned, that's called the Lyapunov function. So we create the Lyapunov function for this system, and we will see if you are, so we said that if you are able to create a function something similar to the energy of the system, if that such kind of function if you are able to create for a given system, then we can say that that system will not have any closed orbits. So here also our aim is to say that here the system will not have any limit cycles or chaos. So for that, what we do is, so as we have said, Lyapunov function is a generalization of an energy function which can represent the different energy functions. And since we have said last time that there is no way standard way to find a Lyapunov function, but the standard method people use is, here we consider the Lyapunov function V as sum of squares, that is 1 by sigma times x square plus y square plus z square. So 1 by sigma, why it is, we will just, as we are deriving, we will see why it is used for. And so if you visualize this, it's like you have an ellipsoidal surface, and this is your x-axis, this is your y-axis, and this is your z-axis. And as you are going, your volume will decrease. That's what we were saying. So your volume, it remains, it decreases. And now, so in r is less than 1 and x comma y comma z is not equal to the origin, then v dot should be less than 0 along trajectories. That's from our standard definition that we have considered, saying that the system is a dissipative system. So that means the trajectory should be moving to the lower v. So if your wall is here, it should be moving towards the lower potential. So that means in actual scenario, you had a volume like this. This volume should be going down. So that means your volume should be eventually shrinking down. So after a certain time, you will be coming down to this state. But there is a limitation on the volume. So volume is bounded by 0. You can't have below, negative volume you can't have. So volume is bounded below by 0. So your volume, as x of t tends to 0, x of t tends to 0, your volume also tends to 0. That's what from the dissipative system concept which we have learned. Now, so we had a, now we need to, so we said that v is a function of sum of squares of this x square, y square and z square. Now we need to find the v dot to prove this. So what we do, we take a derivative of this v dot, so it's nothing but 1 by sigma times 2 into x dot plus 2 into y dot, 2 into z dot. Now if you take the 2 common down, then you are left with 1 by sigma x dot plus y dot plus z dot. So from the equations, you can substitute x dot. So x dot is nothing but sigma into y minus x. This is Lorentz equation thing, and y into rx minus y minus xz plus z into xy minus bz. Now if you rearrange this, you will see that the sigma gets crossed over here, and you will be left out with yx minus x square plus ryx minus y square minus xzy plus zxy minus bz square. So this can be rearranged and wrote as r plus 1 times xy minus x square minus y square minus bz square. Now we can just combine these two things inside, and we can write that as minus x minus r plus 1 by 2 y of square. So we are just rearranging it into sum of squares terms, square minus bz square. So if you observe, these are all squares, and so that means your v dot, if your r is less than 1 and x, y, z are not equal to 0, 0, 0, that is the origin, it is certainly not positive because all are negative and these are all squares, sum of squares. So v dot is less than 0. So now this was the one of the cases which we wanted to see. So once v dot is 0, when we say this establishes our claim that for r less than 1, origin is globally stable. So that was our motive in doing this. And now for a particular case, if we look into, so once we know that, okay, so we will talk about the attractor now. So there is one concept called Lyapunov exponent, so we will talk on that. And so what it means is, say you have two different trajectories which are starting very close to each other. Okay, so we'll write here as nearby trajectories, how they are evolving. If you see, so you have two trajectories which are starting at two nearby points, but over a time if they are separating out, that is, they are having a very strong sensitivity on the initial conditions. So it's like if you are having two different trajectories which are starting at two different points, but they are very, very close to each other. And so our interest is like, can we predict this long-term prediction of this trajectory? Is it possible, or is there any uncertainty associated with it? So in order to study that, so what we do is, suppose we let that initially, say we are decaying the transients and or we are not considering for any attractor. We say that the system is steadily evolving, and say you have x of t is this attractor for a time t, and consider a nearby point which is at x of t plus del t. So that means this distance is del t. So you are considering a point, starting point, and you are having a trajectory which are very close to it but separated by a distance delta t, and this delta t is a tiny separation. It is a tiny separation vector of, say, initial length. We are considering it as, we are saying it is very, very low, so this is of the order of nearly 10 power minus 15. So that much high precision we are considering. And now we will see how this distance evolves. That's what how this del of t grows. If it grows exponentially very further, then we will be not able to predict it properly. So are we getting that, is what we are going to see. So in Lorentz system, we find it is find that this distance from between two trajectories is proportional to the exponential to the power lambda t. So it grows exponentially is what they found, and they found that lambda is approximately equal to 0.9. So what this means actually is the nearby trajectories, if you are starting somewhere here and with a high precision of 10 power minus 15 also, if you are starting, the nearby trajectories, they separate out exponentially fast. So they separate out exponentially fast. So this is, so if we try to plot a graph of this and analyze it, say this is your log of del of t and this is your time. If you plot, you have a negative slope initially, that is your, these values will be going up and down here. It will have a slope. This slope is our lambda here, this slope is our lambda, and the del of t, ln of del, it changes like this, but over a time it will go and settle up on this point. So we will say why this is happening. So there are certain characteristics that we need to observe here. The first one is the curve is nearly exactly straight, or when you are drawing a, if you can plot a curve fitting when you are doing, you can draw a straight line for this initial parts along this. So this is like what we mean by this straight line fitting is the it wiggles around the trajectory is what we say. Okay, so just write it down. So by that, the curve is nearly exactly straight. It has wiggles because the strength of the exponential divergence varies somewhat along the attractor. So that was one thing, and main important thing is the exponential divergence, why it is coming like this and it is saturating at this point. So this is because the divergence or the this separation which we are saying here, this can go up to the diameter of the attractor. Maximum it can go up to the diameter of the attractor. So beyond which it does not make any physical sense. So that's why your system will, the del will increase up to a certain time and eventually it will go and saturate up to a particular point. So this is called the leveling off, we say. So it levels off at this region, and then this lambda is what we call the Lyapunov exponent. So this Lyapunov exponent has the properties like, when you are having a large t, the diameter or the ellipsoidal which we have drawn for it previously is controlled by motion. So if your Lyapunov exponent is positive, we say that the ellipsoidal is being mostly it's increasing in its thing, or it's diverging very fast out. And for when you are plotting the different, say you have different Lyapunov exponent values, we consider, when we are saying that a Lyapunov exponent for a given system, we are actually considering the largest value among these different Lyapunov exponents for a given system. So if you if somewhere specifies a particular value for Lyapunov, it means that it is the largest Lyapunov exponent for that given trajectory. Now, so this significantly means one more thing in this system. So that's like, if you are starting from somewhere here and over a time, if you are going like this, your prediction using this equation will go in somewhat in this direction. So this is the reason why predicting or weather prediction was such a difficult task, was because of this sensitive dependence on these initial conditions. Even a slight change in the initial condition, your trajectories will move out in different ways, and predicting them for a longer time was difficult. Also, longer time predictions were difficult at using this. So the simple Lorentz system was able to predict for a very short time, and so this was the region up to where it's, so we say this t is equal to t horizon. So this t horizon up to which you can predict is approximately of the order of 1 by lambda times the log of a by. Now say this a is the true state of the system and del naught is the initial condition. So we will do one example to understand that. Just within few seconds we will do that. So okay, we will do that now itself to understand what I'm saying. So say you have a chaotic system and its tolerance value or the true value which we are searching is within 10 power minus 3, and our initial state has a uncertainty within the order of 10 power minus 7. So you are starting with such high in accuracy you are starting now. Now our question is, for how long can we predict the state of the system? So for how long we can predict the state of the system? So basically we need to find the t horizon here, and but before that, if there is a increase in the accuracy, say we started a remains same but we use a very high accuracy methods and all, and our accuracy goes to 10 power minus 13. It's like our initial condition difference between two trajectories which we are saying, the initial condition change is 10 to the power minus 13. Now if we are increasing, then how long can we predict? So our basic question is, if your accuracy in giving the initial condition, if it is increasing very, so it's like more than 5 orders it has increased. So if with such high accuracy, if we are doing the conditions for a chaotic system, is that useful, or what is the case in a chaotic system is what we are checking here. So if you find that t horizontal or horizon is nothing but 1 by lambda times ln a by norm of del naught. Oh, sorry. Okay, so the t horizon, it is nothing but 1 by lambda times ln a by norm of del naught. So in the initial case, lambda, let it be there, a is nothing but 10 to the power minus 3 it was, and norm of this was 10 to the power minus 7. So this is nothing but 1 by lambda times ln of 10 to the power 4. So if you take the 4 out, it's nothing but 4 ln times 10 by lambda. So this is one case. Now when your norm of del naught is equal to 10 power minus 13 with very high accuracy, if you are doing the things, then the t horizon will change by 1 by lambda times ln 10 to the power minus 3 by 10 to the power minus 13. So this is nothing but 1 by lambda times ln 10 to the power 10. This is nothing but 10 to the power ln 10 by lambda. So that means when you are increasing your accuracy by, say, from 10 power minus 7 to 10 power minus 13 you increased, which is nearly of the order of 6 orders you have changed, accuracy you have achieved, and you can see that the prediction time increases by only 2.5 times. So only 2.5 times longer you can predict. So such very high sensitivity on this initial conditions is a property of this chaotic systems. So that's why the chaos, if you are someone is asking you the definition of chaos, we say that chaos is a aperiodic long term behavior in a deterministic system system that exhibits sensitive dependence on initial condition. So this is what most of them will be expecting when you are mentioning what is called chaos. Now, by the aperiodic long-term behavior, means that the trajectories will not be settling down to the fixed points or a periodic orbit or a quasi-periodic orbit as time tends to infinity. And since it should be in a deterministic system, that means the system has no random or noisy inputs or parameters. And the sensitive dependence on initial conditions, we have just seen that nearby trajectories, they separate out exponentially fast. Exponentially fast means our Lyapunov exponent should be having a positive value. So these are the key characteristics of a chaotic system, or by the definition of chaos we mean that. Now once we know what is chaos and what is chaotic system, so sometimes it has been seen in Lorentz system that system not settle down to any irregular behavior, or it does not go to a periodic orbit. Instead it winds around certain path, and it never intersects, but it winds around particular path for infinite. T tends to infinity, it remains in this particular region where the thickness of this region is nearly to a zero volume. It accounts to zero volume. So it's like on a plane, but the trajectories never intersect. It follows those rules. Still the system exhibits certain different behavior, and this behavior was after that some point of time people used to call that as attractor. And there is a particular definition for attractor also. So say when you are mentioning something as attractor, so the attractor should be defined as, it should be defined as a closed set A with the properties like it should be an invariant set. The A should be an invariant set. That means any trajectory that starts in A, it should be staying in A for the total time, all time. It should be remaining in that is okay. I will just write it down. So that's like x of t, any trajectory that is the x of t that starts in A, it stays in A in that closed set for all time. It is invariant. So we have something called scale invariance and all. That scale invariance means your scaling properties do not change with your measurement or anything like that. An invariant set means the trajectories remain within that set for any time or the complete time in the system. And for you to say that the system exhibits is on an attractor, the A attractor which we say, the A attractor or the A attracts an open set of initial conditions. It attracts an open set of initial conditions. So A attracts an open set of initial. So if you have an open set of U containing A, then any distance that anywhere you start, all the trajectories that start sufficiently close to it will be attracted towards this open set itself, or this attractor will be coming towards this attractor. Anywhere you start in this set A, it will eventually be coming on to this attractor set, and the largest set is what you call the basin of attraction. So this is what in one dimensional we were seeing. This is the basin of attraction, which is anywhere. So if you remember, we have talked about the rabbits and sheep problem, and the region anywhere you started, it was eventually coming to this sheep region below this line, and if you are starting above here, it was going towards the sheep conditions. So we said at that time, we said that this is the basin of attraction for the system. Similarly, for the basin of attraction for an attractor is any set of conditions where your trajectory start and eventually come to this attractor or a particular form of phase space. If it comes like towards this set, anywhere you start, then we say that that set is an attractor. And the final and important quality of a attractor is the A is on the closed set should be minimal. That is, it should not have any subset that satisfies these conditions 1 and 2. No subset for A should be there that satisfies the conditions 1 and 2. So if these three properties are shown by a given set of closed set A, then we call that set as an attractor. Now to understand that, we can do one example. So say you have an example of, you have a system of this equation x dot is equal to x minus x cube and y dot is equal to minus y you are having. So say we take an interval between minus 1 less than x less than or equal to 1. Now our first question is, I is if it's an invariant set or not. So within this interval, say this interval is what we call as I. Is I is an invariant set or not, we should check. And does it attract an open set of initial conditions, was our second condition, was the second condition here. And third was, is it having a subset or not. So we will be checking all these three now. So if you plot the diagram for this, so y dot equal to minus y, we know anything that starts will be coming towards the fixed point. So here if you solve it, x dot equal to 0, you will get x minus x cube equal to 0, x into 1 minus x square equal to 0. So x equal to 0 and x equal to plus or minus 1 are the fixed points here. So x equal to 0 sorry, and minus 1 and plus 1 are the fixed points for the system. Now since you can find the Jacobian and you can tell the which are the fixed points and all, so I will just go directly, and so if you do that, you will get that these two are the fixed points, stable fixed points, and this is a saddle node. That is, trajectories to in one direction it will be coming towards the system, and in other direction it will be moving away from the system. So if any point starts here, it will eventually be flowing like this towards this fixed point, or anywhere it starts here it will be going, or anywhere it starts here will be moving towards it. So this is the phase portrait for this system, and we know the fixed points and saddle nodes for them. So I is an invariant set as any trajectory that starts in I, that is between minus 1 and 1, it forever it remains in this particular minus in this region, minus 1 and 1 only it reaches. Anywhere it starts, it eventually comes to this fixed points region. So it is within this invariant set I. And so our first condition, that I should be an invariant set, it is satisfied. And second was, it says I should be attracting on an open set of initial condition, that is, it attracts all the trajectories in the xy plane. So anywhere you start, it will be attracted towards either to the plus 1 or minus 1. So we can say that the attractor A, it can be considered as an attractor since all the open set conditions are also met. So second condition and first condition both are met now, but still we can't say that I is an attractor. This is because I is not in the minimal. The stable fixed points plus or minus 1 are the proper subsets of this total I. So this is our, say this was our set I. If you consider this as our I, this minus 1 and plus 1 are all subset of this I, which can satisfy both the 1 and 2 conditions. So these points are only the attractors for the system. So that means you can't, for this system you cannot say that your system has an attractor for your system. So it can either have only fixed points or stable saddle nodes only it can. So it will not show any irregular behavior. That's what we want to finally say in this system. So that's why I mentioned here clearly that A is minimal is a very important condition that needs to be met for any system to be mentioned as an attractor. Now there is one more terminology called strange attractor. So by strange attractor, what we mean is strange attractor to be an attractor that exhibits sensitive dependence on initial conditions. So the attractors that exhibit sensitive dependence on initial conditions is what is referred to as strange attractors. And by the word strange was in the starting times when this was discovered, it was called strange because they exhibited a property called fractal behavior. And by fractal behavior, what we mean is, we will discuss in detail what are fractals and all. It's like on different scales your system repeats its structures. That's what we call as fractals. And fractals have a non-integer dimension. So by non-integer, so our square is dimension 2, whereas our sphere is dimension 3, or a cuboidal if you take, it's as a dimension of 3. Whereas these fractal systems will have a non-integer dimensions, and Lorentz system is said to have a fractal dimension of 2.09, nearly that I believe. So it's said that Lorentz system has a fractal behavior in this system. Now we will move on to the next small topic called Lorentz map. So are you able to understand, or I am going any fast, or these are, yeah, okay. See, these are theoretical things. Once I say this, if you are looking back the things, you will be understanding that. That's why I am mentioning that. So we will just look into a topic called Lorentz map. So when Lorentz was plotting his trajectories, he plotted the Z and Y plot. When he was plotting, he saw a very different dynamics that the system was exhibiting. So it looked so I am roughly drawing it. So it looked somewhat like this, and it switches its plane and it moves towards, so it never crosses the trajectories. That's the important thing to be noted here. So it's like if you turn this into a 3D view, you will see that these are actually like this. They are not overlapping each other, but they are moving side by side beside each other. So what important thing was, it was not able to prove that there is a strange attractor or a attractor the system is exhibiting, having some attractor or not, or this kind of strange behavior it is showing or not. At that time it was difficult to prove. So for that, what Lorentz did was, so he took the time series of Z. Say you had a time series of Z here, and you have a time series, say it looks somewhat like this. What he did was, he took the peak of each of these localized, say this is Zn, which is the local maxima of Z of t. So this is the local maxima of Z of t, and he used this next point, that is Zn plus 1. He tried to predict that thing. So what he did was, so he created a, what we will be discussing in few next minutes is what we call the maps. So he plotted the Zn here, and the next plot he plotted on Zn plus 1. So if you draw a 45-degree line here, I will discuss why this 45 degree is important in short. So actually what it was like, this is like a function. So if you are having this z nth point will decide the z n plus 1th point. That means z n plus 1 is a function of z n. So this is what we call it as Lorentz map, and he was able to show that when he fitted his different points, all these points they organized in a particular fashion like this, and he was able to explain his different states using these maps he has derived. And from here we will look into what we mean by maps, and we will go to the next topic called one-dimensional maps. So we will understand what are maps, then only we will understand what he was able to, or what he conveyed through his maps. Yeah, so we will look into the topic called. So now initially we will be looking into one-dimensional maps. So in the starting class we have mentioned that we are concerning about time in two different ways. Either you can consider time as continuously varying, or time can be considered as a discrete time. So in maps we consider time as discrete. So that's the basic difference from a continuous system. So dynamical systems in which, I will write it down. So dynamical systems in which time is discrete rather than continuous, we call those such kind of systems as, say, these kinds are also called, such kinds are also called difference equations. In continuous thing it is called differential equations. Here they are called difference equations, or we usually refer them as maps. So what we mean by map is, say, a simple example given in the textbook is usually like, if you take a value x0, and if you in your calculator if you put the type saying that cos of x0 if you give, and you keep on repeating this, say you got a value for cos of x0, now that value you give again for that cos of x0 if you give, and if you are keeping doing this, this is what is actually called a one-dimensional map. So this is nothing but your next point is a function of cos of xn. So this is a simple example of one-dimensional map. That is, xnth point can be calculated from the xn plus 1 can be calculated based on the xnth point which you have. And these difference equations are important because this can be used in models of natural phenomena. So a lot of scientific electronics, the digital electronics nowadays, they use this discrete phenomena, and so we will discuss one of the important equation called logistic equation. They all can be more, because discrete time studying is more comfortable when compared to continuous things, and representing chaos in discrete term is more easier, and studying them is also more easier with the maps. So maps are, in practice, they are very helpful in understanding them. So what we will do first is, we will take a simple equation, one-dimensional map, and we will try to do the linear stability analysis on it, and we will say when our system is having a fixed point, or when our system is linearly stable. So these kind for a maps, we did it for continuous system, we will just look it for maps also. So we will take a general equation, say xn plus 1 is equal to f of xn. This is our general equation for a map, and to find a fixed point for a map, we need to say that, so fixed point for a map, what it means is, you are starting at a point, and after the function applying, say you have some cos of function, after applying the cos, you are again coming back to the same point. So that's where we say that it's a fixed point. That is, over the iterations, you are remaining in the same remaining on the same point. Now, so how to, when you are having a equation like this, to find a fixed point, for a map, what we do is we equate this f of x star equal to x star. So this is the condition now you need to meet to get the fixed point for a map. So if you go with this, so f of xn was our condition, so f of xn should be equal to f of x star. This should be equal to the x star. This is nothing but x of n plus 1. So this means at each iteration you are coming back, all the future iterations you are remaining at the fixed point x star. Now here, if you remind the importance of the 45-degree angle, if you see, so this is the line where y equal to x condition is met. That is, if you put xn and xn plus 1 here, xn plus 1 equal to xn is the condition where you are having a straight line joining the that's the diagonal here, and this is the reference line, or this is the line where you are having fixed points. So we take all the reference using this diagonal line of 45-degree in the maps. So that's why till now I didn't say why we are considering a 45-degree line. So this is the reason why we are considering a diagonal line as our reference for studying the maps, because this is the line over which you are having fixed points. Now, to determine the stability of these fixed points, what we do is, as we have done similarly previously, what we did, we induce a perturbation, or eta perturbation we introduce into the system. So this is the perturbation, and we will look into how this perturbation, if it grows or if it decays. Based on that, we can say either the fixed point is stable or unstable. So in order to do that, so in this case you have xn, which is nothing but the fixed point plus some eta you have, and so now if you have this thing, so the xn plus 1 will be nothing but x star plus eta of n plus 1. So this is nothing but xn plus 1 is nothing but f of x star plus eta of n. So if you do the derivative of this, or if you put the Taylor series expansion, which we did previously also, this is nothing but f of x star, f dash of x star times eta plus higher order terms of eta square and all will get. Now in linearization, if you remove the higher order terms, and f of x star is nothing but x star plus remaining thing f of x star times eta of n. This is nothing but x star plus eta of n plus 1. So that's what we have written. So from this, x star goes and we are left with eta n plus 1 is nothing but f dash of x star times eta n. So your perturbation in the next iterate step will be depending on the slope of this f function times the eta of n, and this f dash of x is called the multiplier, or defined, shown by the lambda. So if your lambda, that is mod of lambda, that is nothing but mod of f dash of x star, if it is less than 1, then eta n tends to 0 as n tends to infinity. So you can say that your x star is a linearly stable fixed point. Now in the opposite case, if your lambda, that is your mod of f dash of x star, is greater than 1 as n tends to infinity, then we say that it's an unstable, is linearly unstable fixed point. So we will just look into one of the examples and see how to use them. So if you look into the example, say xn plus 1 is equal to xn square. Now we need to find the fixed points for this and determine the stability of it. So to find fixed point, what we do is xn square is nothing but xn, or you write it as x star square is equal to x star. So it can be either x star is equal to 0 is a fixed point or x star is equal to 1 is a fixed point. Now, so you got the fixed points for this system. Now you need to find the stability. So that for that you take the lambda, that is nothing but f dash of x star. So f of x is nothing but x square here. So f dash of x is nothing but 2x. So it's like 2x star. So at x star equal to 0, if you see, your lambda is equal to 0. So this is less than 1. That is mod of lambda is less than 1. So it is stable fixed point. And similarly at x star is equal to 1, your mod of 1 is 2. That is greater than 1. So it is unstable. So this is how you find the stability of a map, one-dimensional map when we are given. And yeah, so now understanding these maps using these equations, it may seem little difficult, but there is one diagram which I have introduced in the previous one, which we call cobweb diagram. So using this diagram also we can find the different points or different solutions for the system. So how cobweb is drawn is, say you have a equation, say xn plus 1 is equal to some function f of xn. Now you plot the graph between xn and xn plus 1, and as a reference, you know diagonal is our reference every time, and say your function f of x is x square or something, it has some square, it's a function like this, xn plus 1 is equal to f of xn. This is the function it is going. Now we start at x naught, any point, and you move up to the point where it interacts the curve. So this will be your next point, x1. So you found x naught and you are now finding x1 you got. Now to find the next point, you need to go up to this, or you move horizontally up to this point where x star is equal to xn plus 1 is equal to x. So this is the point, the line that here, and now you move in the vertical direction. Now the point where you meet in the second is what your x2 is. So that you will get x2, and similarly you can move in back and you can get the different values of x0. So once you know the x0, you can find the values of x1 and you can find all the other points in the system. So that's how you create a cobweb diagram. Now for a simple example, say xn plus 1 is equal to sine xn. If we try to plot the cobweb diagram for this, and we need to say that x star is equal to 0, that is our origin is a fixed point. What is the stability at that fixed point is what we want to see, and you can do the linearization method and you can find that. Apart from that, if you do that linearization method, say x star is equal to 0, so sin x equal to 0, if you put x sine of x 0 is 0, so x star equal to 0 is the point if you are considering. And if you consider the f dash of x star, which is nothing but cos of x star, which is nothing but cos of 0, which is nothing but 1. So f dash of x star equal to 1. So we have learned about the conditions where f dash of x star is less than 1 and greater than 1. But f dash of x star equal to 1 is the marginal case. This, if you remember, in the continuous term also we did this, and the marginal cases were what we talked or called nonlinear centers. We said that if there is perturbation is little higher, your centers will go to either spiral or unstable spiral or stable spiral. These are the cases which we talked when we were on the boundary line when we were there. So this region when we were there, we were saying that your system can go from centers to stable nodes or unstable nodes. So this was the marginal case, and now we see that in maps also you are having this marginal case. So linearization cannot do these marginal cases, but using the cobweb diagram. So for this, if you draw the cobweb diagram for this, say this is your xn and this is your xn plus 1, and this is your 45-degree line, and sine wave is like this actually. So from 0 it starts and it moves like this. Okay, just draw it properly. So this is your sine wave, and if you start somewhere here, say x0 is somewhere here, you move up. Okay, I will draw it with a different color to understand. So you start somewhere here and you move up like this, and to get the next point you need to move up. You got here, you need to, this is our line, so you got up to here, then you need to move horizontally, then you need to come down. So this is your second point, and then you go here and then you come back. So eventually your line is decaying down, and you are seeing that this is value is decaying to this 0. So that means your 0 is a stable fixed point for this map. So our marginal case was not able to say anything, but we were using the cobweb diagram, we can show that x star is equal to 0 is a stable fixed point. This is because over the time, if I draw it little more zoomed version, say this is your line and this was your curve, if I say. So you were here, you went up here, then you came down, then you went here, then you, so you are eventually progressing down to this point. Eventually you are coming down to 0. So anywhere you start, you are coming back to the 0th point. So that's why we say that x star equal to 0 is a global fixed point. And I will show you in software how this can be visualized also. And so if we consider another example, say xn plus 1 is equal to cos of xn. Now we need to find xn, how it behaves as n tends to infinity, how it behaves if you want to see. So here we will also draw the diagram for that first. So here we are plotting xn and xn plus 1, and cos term goes like this, it goes, and this is how cos behaves. And if you have a 45-degree line over here. Now if you start somewhere here, if you now you start somewhere here, you go here, so this is your first x1, and now you need to go to the diagonal line. So you went here, now you go up to get the second x2 value. Now you got the x2, now you need to move horizontally to get x3, so you went down and you need to go to this second point, so you reached this is their x3 value, and now you need to come here back to the diagonal line, and you need to move up to get the x4. So this was your x1, x2, x3, and this is your x4. Now you need to move horizontal towards the diagonal, and you need to come back down here. So now if you observe, you are now under a spiraling, you are doing a spiraling over this particular fixed point. So if you observe clearly, you are spiraling towards this fixed point. So this can be experimentally, you can test it by, if you put a value, arbitrary number for cos, and if you do this on your calculator, if you go on doing this, you will see that your system, your value eventually it goes down to a value nearly of 0.739. Some decimals will be there remaining. So you will be eventually reaching to a particular point called 0.739 value. So this, as n tends to infinity, your system is going to this particular stable fixed point. So you can just test in your calculator. So as number of iterations you are increasing, you will eventually, so this thing, it is like it's looping around like this, and it's eventually going to this particular fixed point. So this spiraling is what we actually called as damped oscillations for a map, 1D map. If you consider your system even damps or provides oscillations and eventually damps down to the lower value, and the fixed points, the lambda values for this is always less than 0, a stable fixed point. For So since lambda is less than 0, you will see a damped oscillations. If your lambda was greater than 0, you will see that a monotonic decay was there. That is, eventually your sine wave will come eventually faster to that fixed point, not providing any oscillations like this. Now we will, so I hope that is clear, and so we will move on to a very famous map called logistic map. So this is similar to the logistic equation which we have dealt with. It is nothing but x dot is equal to rx into 1 minus x, or you had x by n and all. In logistic map, what we have is x n plus 1, that is n plus 1th generation population is a function of some growth rate times nth generation population into 1 minus x nth generation population. So this equation is what you call as logistic equation, and if you try to find the fixed point for this, say rx into 1 minus x, if you do, equal to 0, if you put either x equal to 0 you can get, or r into 1 minus x equal to 0, so x equal to 1, either of them you can get. So x n plus 1, so when you are drawing the Cobb diagram or when you are plotting this diagram, so your x n goes from 0 to 1, whereas your r value, so you need to find the maximum of this. For that, what we do is we find the f dash of x to find the maximum. So it is nothing but r into 1 minus 2x. If you equate it to 0, you will get that x is equal to 1 by 2. So when x is 1 by 2, what is the value of r? So this is our equation, xn plus 1 is equal to r xn into 1 minus xn, and if xn is half, so this is half into 1 minus half, so it's nothing but r by 4. So your maximum value that your system can have is r by 4. So your logistic equation, if you remember, this was something like this, and this is the maximum point, r by 4 is your maximum point. So we plot graph between 0 to 1, so your r values range from 0 to 4. So 4 by 4 you will get 1 there. So this is done so that you map onto the same point, xn plus 1 and xn, you map onto the same points. That's why they are shown like this. Now the interesting characteristic of the logistic map is, when you are having r is less than 1, that is your growth rate is less than 1, the population always goes to exit. The population always goes to an extinct. So when your growth rate r was less than 1, the population, so in the Cobb diagram, if you see, population always goes, xn tends to 0 as n tends to infinity. So anywhere you start here, eventually you will dampen down. So the earlier diagram which I showed, you will go down to the point here, it will go to the 0 here. Whereas if your growth rate is between less than r less than 3, there are different dynamics the system shows. So if you plot the time series for that, and for a particular case of r is equal to 2.8, if you see, your diagram looks somewhat like this. It moves and it settles down here. Okay, so instead of drawing this, I will show you how this behaves. That will be more, you can understand it more. So I hope my screen is visible. So here now I am, oh, it has not come. Oh, but on my screen, oh, Malvika, you are able to see? Oh, okay. Maybe within few seconds it may come. Maybe net is slow there. Yeah. So this is one of the, okay. So this is one of the simulators of logistic map, where you can draw the Cobb diagram and all, and you can see that when you are putting less than one value, say it's you are putting 0.8, and this one, it is the number of initial items. If I put 1 or 2 or 3, you will get more number of lines starting at different points. And initial condition is 0.2. Here you can start x0 at 0.2 or anywhere you can start. So if you start the animation, you will see that the system moves like this. So initially now, okay, we can't reduce the speed here. Okay, now when I am, so instead of that I will just show the R values here, say 0.8 it was. If you put the 0.8 over here, so this is one more app which shows how your logistic map grows and it comes. So anywhere you start over here, when your R is less than 1, you can see that your system eventually goes to the 0. So x star equal to 0 is a fixed point, and it's a stable fixed point which we are able to show. Now when your R is between 1 and 3, say you take 2.8 if you are giving, and if you are plotting it, so you can see that you started at 0.2. So if you see the time series here, you started at 0.2, you had some small minimal oscillations, and eventually you settle down to a particular point. Now in cobweb diagram, if you see, you started at 0.2 and you eventually start growing, and it will eventually you will be spiraling and you will be coming to a fixed point. So that's the point that is shown by the straight line here. So actually you can't join the lines here. Lines doesn't mean anything in discrete points. Only the points, nodes which I am showing here are the practical things. Lines you don't need to consider. This for understanding just how the time series evolves. For that only they have connected the lines. So when R is between 1 and 3, you will see that the system eventually comes to a particular point after the oscillations. Now when your R is greater than 3, say it is 3.3. Now if you observe, your time series looks like this. This is called period 2 cycle, where each cycle repeats after 2 points. So if you start here 1 and 2, the next point will start at 1 and 2. So it's like after 2 points the cycle is repeating. And if you look in the cobweb diagram, you will see that you will have two different oscillations. So you will go like this, and you will have a oscillation over here, one, and you will go one more time in the different path here. It's like you have two oscillations over here. Okay, I can't zoom there. So you can see that the system bifurcates at the bifurcation diagram. If you look into the red line is where we are now. You can see that there are two different solutions for this at a particular point. That at R equal to 3.3, as you are increasing your parameter R to 3.3, you will observe period 2 oscillations in the system. That is, in the cobweb you will be two oscillations will be moving up and down here. That's how you visualize in cobweb diagram. We will talk of this bifurcation diagram as we are progressing. So now you can see that initially your system was at 0 and you bifurcated to one particular point here. You were having a one fixed point up to 0, and as your R is increasing from 1 to 3, you had a fixed point that is particular to that particular point it was remaining. So at 2.8 we saw that your system was coming to 0.6 or nearly. Now at 3 your system bifurcated, and now your system shows two different points. So two different cobweb, in the cobweb itself two different oscillations you can see, or in time series this means it repeats after 2 cycles. It's called period 2 cycle. Now when you are increasing your R to 3.5, so you were initially 3.3, now at 3.5 if you see, so now you can observe that system is behaving, it's showing a period 4 oscillations, that is 1, 2, 3 and 4. After 4 points it is repeating its cycle. So when you are moving from 3.3 to 3.5, system started, it bifurcated again, and now if you observe the bifurcation diagram here, you can see that there are two further bifurcations happened there, and you are having 4 different fixed points over here. So in the cobweb diagram you will see that there are 4 different loops onto which the system will come and go. So it will be coming like this and moving, it will be going, so it's like 4 oscillations it will be doing around this loop. That's what we call by period 4 cycle. By period 4, okay, in other means period 4 means you will be passing on through 4 different points after a repeated number of cycles. So here he did 50 iterates, and in 50 iterates you will be repeating these particular 4 points back to back again and again, and that's what you call as period 4 cycle. So you initially started with period 2, then you came to period 4. Now if you go on furthering, you will see that the period doubling bifurcation happens, and if you increase further and further, so if I will show one more value, say if you are increasing to, so initially it was 3.3, now it was 3.5, and now the values are also becoming very close, and if I give a very specific value of 3.54409, so you will observe a period doubling bifurcation where your system will now go to 8 particular points. It will repeat after 8 points. So 1, 2, 3, 4, 5, 6, 7, 8. So this many points, after that only it will repeat the pattern. So this period 4, and okay, now here we are very close to this point. You should be moving little bit more. So this zoomed version is shown in the down where I am showing the arrow cursor. So you need to move a little bit further for this to show period 8 bifurcation. So currently we are in the period 4 only. So you can see that you will have, so the zoomed in version has 4. Apart from that, the zoomed out version will have further 2 down. So it's like 8 by points you need to repeat the cycle back to back. Okay, here it is period 4 cycle. So you need to little bit more, you need to give the value. So our basic interest is like you are going from a period 2 doubling is what you call. So it's like you are going to a chaotic state, and for chaos, say if you are giving a value of 3.9, if you give, so now you can see that your oscillations, they are very chaotic. They don't repeat any themselves. They are fully random, and you can see in between there are different dynamics which is shown by the system. And the cobweb diagram also shows completely the system is not moving at a particular loop. It's going up and down. It's moving completely randomly there. And in the bifurcation diagram, if you observe, this is the point where you are having complete chaotic region. System has lot of different points through which the system will pass. So in the tutorial 2 we will try to plot this bifurcation diagram also, and how the Lorentz map can be plotted. So this is one of the important one-dimensional map called the logistic map. Okay, we have only 4 more minutes. So we will do the analytical things in the next class, but so logistic map is an important, and we saw a route called the period doubling route to chaos. So we saw period 2 here, then period 4, then we successfully went to period 8, and it will go on like this, and eventually you will come to a chaotic state when your parameter reaches to 3.9. And in the bifurcation diagram you can look into that completely, and if I give a very high value, say 5, if I give, okay, so the map goes to very high things, you will go to 4. So once it goes to very high values, you will have different maps called Henon map. And so now you can see their bifurcation diagram, and it's more and more closed form. Since 4 you have taken, that's a particular point at this end, that's why you are having a closed form solution for that. And so bifurcation diagram, if you observe, you had a fun beam here, then it bifurcated to 2, then 4, then 8, and it goes, and this very dense region is where you have a lot of bifurcations happening. So this is called a period doubling route to chaos. So logistic map exhibits a period doubling route to chaos, and lot of real world systems. And in real world systems, people have shown that period doubling route to chaos exists, and there are experimental evidence showing that. And if you look carefully, you can see that in between this you are having a periodic regime. So in between these chaotic regimes you are having a periodic regime. So this is period 3 bifurcation or period 3 cycle. So for that particular period 3 cycle, the value of R you need to give is, just look to the value, how much you need to give for R. Okay, R value. Okay, so I will just look into that, how is the value. So it was 3 point, okay, it was periodic window value, it is 3.835. It's like 3.835 if you give. In between that you should be able to get a period 3 window you will be getting. Yeah, so we are exactly at this particular line, and you can see that it loops. The darker line, you can see it is 3 dark lines you can see over here. So these are the 3 points which it moves, and your system repeats after this particular 3 points. Not particularly 3 points, it does not repeat, but it will have different. So if you are having a period 3, we will discuss in the next class, you will have 8 number of solutions to it. And so these different solutions, they all will not exit, only particular 3 points you will be repeating back to back. So that's why we call that as period 3, and you will be seeing in the bifurcation diagram this period 3 region. So okay, so I will stop here, and next class we will discuss this period 3 and logistic mapping solution, how analytically what are these and what is period doubling, bifurcation and all, we will discuss in the next class. Yeah, tomorrow. Yeah, so was it understandable, or it was I think first I little bit explained about the water wheel and all, because Malek was not there, so I just explained the water wheel and all the concepts. Okay. Okay. So Malek, you were able to understand? Okay. So we will discuss in theoretical aspects of this logistic map, and we'll complete this 1D maps and fractals we will start. Yeah. So in next class we will do that. Yeah. Thank you. Good night.